Hi, welcome to Foundations Linux, Distributions and Building from Source. My name is Dennis. Let's get started about what we're going to learn today. Our learning objectives include being familiar with different distribution features. So, the differences between Debian, Ubuntu, CentOS, Red Hat, we need to know and we might be able to use all of them above in our solution. Ultimately, we need to know some of the main key features. We also need to interchange different administration commands between the distros and be ready to recognize when we need to use one or the other. Now, fortunately, you'll be able to use many different commands as shared. Some commands are a little bit different, and so you should keep that in mind. Finally, we'll be able to use common tools to build and compile applications without packages so it can be completely portable between different systems. Let's get started here. Now, one of the main differences between Linux and many forms of Windows or even Mac OS X is that we have the idea of distribution flavors. Now, we're using Ubuntu in our current learning environment, but you can also use Mint, Kubuntu, Xubuntu, and many different other ones that are Debian based. There are other ones that are on the left side of this, which is more on about Fedora, Red Hat, Arch, um, and really they have different needs and different use cases. So we're using a fork of Debian, which is Ubuntu in this case, but there's many others, and some of the commonality between all of them is really things like Red Hat and Fedora utilize the Yum package system and whatnot. Ultimately, the differences are all about use case needs and environments. Debian is great for a community that has lots of support for security and networking and different packages. CentOS, Red Hat, Fedora all use Yum packaging and are focused around server-side stability across the environment. So they rather have less bleeding edge packages and more stability and ability to roll back, have some of these enterprise features that is missing natively from Debian without third-party packaged resources. You can explore different options on different flavors of Linux depending on what your needs are. Are you an end user? Are you using a server? Or perhaps you're just using this to experiment and deploy code on. All up to you. Please feel free to read up on this on the links inside the student guide. Now, as mentioned earlier, package managers are a huge deal. We saw the failure earlier in different sections, how Debian using depackage installation without the proper dependencies completely hosed our ability to install Wireshark properly without cleaning everything up. In that sense, using package managers makes the most sense. Most of our builds, including Debian, like to utilize the app package manager. And we'll use that right here. And apt is by default using Kali, Ubuntu, and other Debian-based builds. CentOS-based builds, such as Red Hat Enterprise, Fedora, Oracle, and even Amazon AMI2 uses the Yum package manager. There's different pros and cons of each one, and that really depends on what you're looking for. Anything with Red Hat based Yum, you can actually roll back easier than you can with apt. Now with apt, if you're doing more bleeding edge packages and security work and networking related work and solutions there, you might use the Debian based distributions for your needs. Now that isn't to say that neither one of them can meet your needs as a whole. It just takes different approaches. And what's similar between all of them as a whole is that they can go ahead and install, remove, update all packages using the similar keyword structures. Now, the only main difference that you might see here is app cache search. Really, that's been updated to app search in modern use of Linux, but app cache might be still the requirement, and app get might still be the requirement in older distributions. So again, Yum is for Red Hat and CentOS and other distributions. We're using Debian-based distributions like Ubuntu, Kali, and apt for our purposes and our tool sets. One of the main features that I wanted to highlight also, and that's something we can't really showcase in our demonstrations, is really some great use cases of Yum. Why would we want to use Yum over apt when Ubuntu seems perfectly fine now? Well, one thing I wanted to point out is that we really want to get to a place where we want to roll back something in case something goes wrong. Now, when something goes wrong, try to get that pin back over here, is that we're looking for history. We're looking for rollback requirements, and we're looking for the ability to really showcase what we're going to do here. So for Yum history, we can see our rollback right here and all the times of alterations without having to worry about parsing a log manually. And one of the coolest things is that Yum package managers can actually do an undo state, right? They have native rollback. And you might be wondering, well, can't app do this too? Not natively. You have to do a lot of different works, and really all you have to do is find your differential change and roll that back. And it's an easier way to have production environments managed for issues such as broken updates, security patches, or other configurations that might have occurred that might have broken your production ready system requirements. Now, language extraction is all about what we do in automation and programming as a whole. Knowing that we have different distributions and code requirements, we looked a little bit in our last lecture about shell scripting. We learned about conditional statements, and we learned about how you can utilize one-liners or in combination with the shell script as a whole and register them as services. We're going to dive a little bit deeper into the code itself and how you can utilize compiled-based code. So shell scripting is interpreted-based code. Your shell does the interpretation for you. You just tell it what you want to do. But really, all language extraction is based on ones and zeros. Remember that machine code, aka ones and zeros, are binary. That's all the computer understands at the lowest level. You are programming things at the higher level. So shell scripts and Python, which is what we see here, which is print hello world to our standard out, that's high level. High level, moving away from native machine language, moving further away from the ones and zeros that you have to be prepared to use with these compilers. Now, what you see right here is actually the same exact hello world print statement, ironically in assembly. So if you were to compile perhaps a C language, C++, or another compiled-based language into an intermediary code, into a binary that you can run, this is what you might debug. And ultimately, you have to do all this to equal this. And if you're wondering why you should use compiled code as in terms of interpreted, we'll see that in the upcoming slides here. But notice that the higher you get, the more simple it gets. The lower you get, maybe the more performant you might get, but the more you have to know about the system, how to address memory, how to address and call things to the CPU, change things, add things to the kernel, tell the kernel what to do. This is a lot of work. So ultimately, a higher level code is really a great place to start for a lot of beginners. Now, we've discussed a little bit about performance and why you should use compiled versus interpret code. We used interpreted shell scripts earlier, right? And that is considered a interpreter-based item. So we have shell scripts in Bash, and we have a source code, which is easily just a bunch of commands glued together. And we might have an intermediary code, but really Bash is doing this interpretation for us. So all that for loops, the whiles, the if-else's, Bash is doing that for us, and it's already built in. And then finally, it has the interpreter, right? So this is all one swoop inside a shell script. In different aspects, such as Python, right? Python and Ruby and JavaScript, this will be sent into an IL from the interpreter. So you have your Python script, such as your print hello world. It goes into the to intermediate code, which gets turned into like assembly or something like that, and it gets forwarded over to the interpreter to make to actually run that into machine code, right? All the ones, get that back over here. All the ones and zeros. Remember, ones and zeros are machine codes. MC for machine code. Python gets translated accordingly into either an intermediary language or directly translated to a machine code ones and zeros from the Python engine. And this is the same or not similar from our shell scripts, but there's a difference between that and our upcoming attempts. So we have, and I put this in the wrong place, my apologies. We have our source code just like everyone else inside our items. And these are like C, C#, Java, Visual Basic. These are compiled code. So basically you have to define everything and then you have to build the code onto an architecture-based system. That creates assembly or object code, which you saw a little bit earlier. And in fact, if you're wondering what assembly is, this is assembly, right? This is saying, hey, at the send me most basic items. I need you to talk about how you get things in and out of the CPU and allocate memory. Very difficult stuff. You build the code at high level, it turns it into assembly code, which is ASM for short. And then finally, it gets translated from the compiler into machine code once it links everything together, and you have a binary after that. And that binary, aka your bin, is your ELF file. So some coders are all about going to .NET, and most people ask, well, what about .NET? Is that a interpretative code or is that a compiled code? Well, the answer is kind of both. And you might be scratching your head going, what do you mean by that? Let's take a step back here. Remember that libraries and DLLs and object files, they're just libraries. They're just references to something because you didn't know how to do it yourself, or you just found out that that person, you didn't want to repeat code. That person just had to do it better, and you didn't have to repeat it by ingesting it into your code and making it larger. So you have external dependencies. The .NET framework is exactly what that is. It's actually a common intermediary language that you can call on in a standard API way. So whether you're using Visual C#, VB, or even C++, you can compile those and exercise and utilize the .NET framework for specifically Windows-based or Microsoft-based devices. So you'll compile your front-end code here, which is your C#, which is still compiled into a exe that can get launched by Windows. And that exe then gets referenced to the .NET framework. That .NET framework then executes a series of commands as interpretative code with a just-in-time, JIT, compiling engine, which then converts that into machine code for your computer to actually utilize. So it actually is a combination of both. And that's why you see many developers have arguments over .NET ease of use and flexibility versus native compiling to machine code. So with C# and many other compiling languages, you can compile natively without the use of .NET. However, if you don't use .NET, you have to understand all these things called syscalls, system operating system calls. In Windows, we call them Windows API calls to the backend. At the end of the day, you have to know a very complex set of calls in C language and be able to make them and have a heavier lift. With .NET, this makes things easier. And so you can actually have two developers working on the same application with different functions and even different coding. One developer will use C# on one side, another developer can use VB on the other side, and they both reference the .NET framework like the same way together and get the same output on different machines as long as it's using the .NET framework. So the answer ultimately is you have a compiled language at the front end that creates a portable executable exe file, if you will, that launches functions directly into the intermediary language, which is .NET. So think of .NET as the version of assembly, where C is when you're doing an intermediary language is compiling. .NET framework itself then uses a JIT compiler, so it actually does compile over time and creates the machine learning, not the machine learning, but the machine code of ones and zeros, just like you did with an interpreter. So remember that .NET towards the end behaves like an interpretative engine. However, whatever you use to program in .NET is actually just a compiled program. And we call that .NET compiled, and that's why when someone says I program in .NET, it just means it doesn't matter what the top programming language is that reference it. .NET, all the slowdown is right here. And so what you have is a hybrid of compiled languages that really act like an interpreted engine, just like Python and Ruby, but it's really still compiled. So you get the performance cons of an interpretative engine, but you get the ability to do compilation and potentially hide your code, unlike interpretive engines using compilation in .NET. So it's really up to you. So if you have code that needs to function on Windows 10, Windows 7, a mobile phone that still uses the older Windows versions, or perhaps even the Microsoft Xbox, it uses all .NET framework libraries that can reference different calls and different compute needs across many different devices. It's quite amazing when you think about it. So ultimately, how do you compile everything natively for the most performance? Well, there are different compiling codes, again, like C and C++ and C#. And you use the compiler. So our compiler that we'll use in our labs and our demonstrations is GCC, which is built into um, the Ubuntu distribution. GCC stands for the GNU C compiler, and ultimately it creates intermediary code, which is assembly, which you saw earlier for our grossly large hello world. And also GCC actually acts as a linker. A linker just basically says, hey, do you have external or system library objects that I have to reference? Do I have to ingest that into the final code, or can I just say reference it to a particular path, such as /lib inside the directory for relative path names? And ultimately, we get a L file that is executable by the operating system. That's all it really means. So all you've been doing compiling all this time is sending it through a compiler. It linked everything for you, and you went on your merry way. Actually, these are two separate functions. So the compiler compiles everything into an IL or an intermediary code, and then the linker could be a completely different program altogether, linking libraries externally or bringing them in internally from external locations. But GCC tends to do both. So we'll see this in the labs. Let's go ahead and get to our first break and demonstration. So go ahead and get your virtual machines spun up and follow with me so you can get the most out of your time here in our lecture. We'll see you then. Hi, and welcome back. I hope you had a great break. Let's get started. Hopefully you have your terminals up and running. Let's dig down into our code and figure out how to compile or use interpretative code to get what we need done. First things first, everyone starts off with hello world. Now I know what you're thinking, we need to do so much more than that. Trust me, it's going to happen. Let's focus on performance and understanding the main differences first. First, let's use Python 3, which is a interpretive language. We'll use a -c option, and we'll create a quotation requirement here. So we'll use print, as we saw a little bit earlier, that print hello world means something completely different. And we'll do this in line, and we'll see how it works. We got our print hello world, and let's figure out what the speed of that is and how much compute time we actually utilize. For that, we use time, and it did a real time of roughly half a second, and it spent this like that. Now let's see if that actually is more performant or less performant than a compiled piece of code, such as C, which is somewhat high level, depends on who you ask. Let's do a vim hello world.c. You can follow along with me. Again, this is not a shell script, this is actual C code. So I'm not expecting you to notice. Just follow along and understand the concepts. Focus on that. This is our simple hello world. So we're going to not put any comments in here so we don't have any kind of size and interpretation differences. We're going to initialize main as an integer because we want to exit as 0. And we're going to say printf hello world. And then we'll also need to include the standard header library because standard in and standard out.h. And then finally, we need to wrap it up with a return statement. So we're going to need to return out a 0 and end our main script here. Okay, so that's a few lines. It's a little bit more work too. But we're not done yet. So we do a file hello world. Unfortunately, it's C text, so we have to go and compile it. So the compiler actually needs to run like this: GCC hello world, and then we need to create the output hello world. Let me say elf here, if you wish. And we said print by accident, and the compiler caught this for us, so I accidentally didn't put the F in there, so we need to print F. Let's go ahead and right quit and compile that accordingly. Now we have a compiled Elf file that linked to everything we needed with 64-bit as we're compiling, dynamically linked, and we're going to run that via time. Time, hello world, and then actually a much greater performance, 0.06 and compared to 0.002, thereby proving that even the most basic hello world statements, direct machine compiling makes the most sense for performance. Same exact thing that happened, took more work, but you did it up front as opposed to not having to compile it whatsoever. Python is going to be more portable as long as Python is installed in other systems. This, however, is going to be, even though it's dynamically linked, the standard in and standard out header file is in most common Linux distributions. So really, this file is now a binary. And if you look at it carefully too, you can actually compile and run it. You can actually just keep it running and copy that to any other Linux 64-bit operating system and run it accordingly. So really, you don't have to have Python installed, which makes it even more high-performing than so. Again, 0.05, 0.010. I mean, there's just really no comparison to the performance. So I wanted to show you really the difference before we got anywhere else towards this. Now that we've had a taste of using the compiler, remember the compiler links different things together. So how do we do this? Well, we look at other things like strace, which is short for stack trace. We'll see if Hello World did any kind of stack tracing, which is cool. And we did do a stack trace, and notice that these are all called. And if you look up different aspects of these, such as mmap and access and fstat, these are all stack traces inside your operating system. So we look at man write, and it's actually a syscall trace too. So man be okay, and change segment size, Linux programming manual, and these are all functions that could be pulled in using the C language option, and these are called syscalls. Okay, called syscalls. If we did an strace as well on the Python, so we go back to our Python. Let's Control R because I can't find it anymore. Python, and bam. Why don't we do an strace on that? And wow, that's so much more stuff that has been added. You have to do stat commands. And really, let's think about this. Let's think about how much more complexity there is between the two. Let's do this first. So let's redirect that to standard out to a file. So it obviously didn't give us what we wanted. So let's go ahead and redirect that to file, Python trace text. And then let's cat Python. Nothing's in there. Interesting. Okay. Well, so we're gonna clear that out. We can touch again, and we can cat that out. Let's just remove it all together. And this is where we come in with T. So because it's not giving us a redirect with standard out properly, we'll use the ingestion with T. And then we'll say the file should be here. Okay, so let's make sure that the Python trace actually worked. Nope, still not really working very well for us. So really a lot of this is not just standard in here, it's actually producing all these interesting messages that have to be interpreted. So let's go forward with our additional learning curve here. Let's do a lab related items here. So for that, we also do a series of different items. We can do a library trace instead. And exit it with a 0 out, which is not bad. Now let's do an L trace of our Python. Wow, lots of different libraries, different things going on, string copies. So it's actually being, you can actually see what's in here. String copy is actually a C term here, and it's actually being translated to machine code, and it's actually giving us an interpretation of that allocation and whatnot. So this may not be a lot to you, but over time, when you're debugging and trying to trace what is going on and what the actual application is doing, you can also run straces and figure out what is kind of going on in the mappings there. One of the other things I wanted to showcase was the idea of checking your source code for errors and bugs. So in the lab, you'll also install CPP check. So we'll have this for help. And you can actually check code for potential errors and security violations that you'll see in the lab accordingly. So I'll leave it to you. Have fun and enjoy. Remember that you can utilize many different items and use GCC using our syntax below, history, rep I, GCC. It can actually utilize GCC for many different needs. And really, the easiest way to use it is insert your C file, -O, and create an output file, and it'll do the automatic linking for you. All right, that's it for today's lecture. Hope you had a great time and learned a lot. We'll see you in the next lecture.